Hello everyone, my name is Nisar Patel and today I will explain you about the assignment 3 of Applied Machine Learning. So let's get started with this assignment. So what we are doing in this part, the assignment 3. So in this one we will learn how the convolution works and how we can apply the convolutional neural networks that we learned so far. So let's get started. So most of the things in this assignment, the boilerplate code is already provided. We have to just play through it and generate the proper result. In the first part, we are importing different libraries that we need in this assignment, such as NumPy, then PIL, import image, SciPy, skimage, matplot library, and etc. Then we are actually importing the image. So this is the link from where we are getting the image, storing it in a response, then just printing what the content of response is. So here, as you can see, it's actually this image that we got from the internet. Then using the NumPy, we will buffer the image into the RAM and then open the buffered image and transform the image into 3D array. So let me just show you this input img array. As you can see, this array is basically the picture or the actual image. So it's a nice looking Lamborghini, pretty good. Now to get the shape of this image, we will use dot shape property, and as you can see, it's 140 by 359. So that's the length and width of the image, and 3 is the channel, so channel 0, 1, and 2. Let's just compare all the channels. So for comparing channel 0 and 1, we will use np.array equal, which will return true or false, either the array or either the channels are equal or not. So 0 and 1, as you can see, it's not equal, so false. Channel 1 and 2, they are also not equal, so again false. Now moving ahead, we need to save the color channel 0 into the input img array variable and print it. So to print the channel 0, we will use this property, which is the array of all the rows, columns, and channel as the 0, and then printing it using the plot.im show. As you can see, only the channel 0 is shown, not channel 1 and 2. So now visualize the values inside of the resulting array. So this array, it's all a bunch of the 255s, as you can see here. Now moving to the next part of this assignment, which is actually the convolution with the 2D kernels. To start with that, we need to pad the array. So for that, padded array equals to, we will use NumPy, so np.pad, which is already a method that is provided in the NumPy, and there we will pass our input image. After that, we will define the kernel. So for initially we will put the kernel as this one, and then the output array, which will be zeros, so a numpy dot zeros, and what will be the shape? It would be the shape of our image, so input image dot shape. So how this padding works? So padding will add in total of 2 rows and 2 columns, and each one will be divided. So first one will be at the beginning and the second one will be at the end for both rows and columns. To show to get actually the value of the padded array and output array, and as you can see, originally we had 140 and after padding it's 142, so 2 rows more, and the columns were 359, and after padding it became 361. Now this is the bunch of code that is already provided, which is applying the kernel to the array values. As you can see, it's a for loop which will apply this kernel, and after doing so we will get this output array, and as you can see it's it's a plot, and to make it clear I have used the gray, which makes it easier to understand the difference. Moving forward, we will see what the standard convolution is. This is this squash pixel value which is already provided. Then there's convolution 2D array method which is already provided. I'm not going into this, but yeah. And then in the line detection, what we will do is with the image convolution we can easily detect the lines. So we have to create different type of kernels with different angles. So first will be the horizontal, second is vertical, third is 45-degree, so on and so forth. So for the horizontal, this should be the kernel, and applying that to the image, so transf horizontal, just a variable name, and calling that convolution 2D kernel, passing our image and then the kernel as this horizontal kernel. After doing so we will get something like this. It's not very clear, just a distorted lines. Now in the next part we will create a 45-degree kernel. So for creating 45-degree angle, this should be the values. Doing the same thing as above, defining our convolution with the image and kernel as this the 45-degree. As you can see, it's more clearer now as compared to the previous one. Now increasing the angle to 135, which is the obtuse of 145-degree. So in obtuse of 45-degree, sorry. So in the 45 it's -1, 2 is in the backslash format, but here in 135 it's in, and the 2 is here, 1 and 1. Same thing as we did earlier, applying the kernel. As you can see, we will get something like this. Now in the question 2 we will apply the following kernels to the image and plot the output. So the edge kernel 1 is this 45-degree, which is this one. Then the edge kernel 2, which is 0 1 0 1 -4 1 0 1 0. Applying that, So here the lines are not clearly visible. In the second one, it's now more visible in a clear format. Now the edge kernel 3, in this image it's more clearer than the previous one, as you can already see. Then that's everything for the convolutional part. Now moving on to the actual neural network that we have been doing so far in this course. So for that we will import the necessary libraries such as TensorFlow, Keras, two categorical, sequential, different kind of layers. And then of course the data sets itself, that is CIFAR 10. And the first and foremost we will divide the data set into training and testing images and labels. After doing that we will do one hot encoding, which is using the two categorical and passing the labels. Then we will actually convert these integers to a floating point using AS type method. After that we will normalize our images by dividing it with 255, which is actually the value of the color pattern, that's RGB. After that we will build our neural network. So as you can see in this model, we have in total 5 layers. First of all is the convolutional 2D, which has a size of 32 with the activation value. Then a max pooling layer, then a flattened layer, a dense layer with 128 and activation as value. This second dense with a weight of 10 and activation as softmax. After that we will compile our model with the optimizer ADAM and loss as a categorical cross entropy. After that, printing just the summary of this model. As you can see, it shows the 5 layers as we already defined earlier, with the size of each layer. Then moving forward, it's the custom callback. So what is this callback for? Callback keeps the record of the number of epochs that we defined. So after every 5 epochs it will show what the accuracy and of training and accuracy of the validation is. So after defining that, we will actually build our model, like actually train our neural network. So for that we will use the fit as we do earlier, and this time we have increase the number of epochs as compared to the previous assignments or previous work. So here we are doing 50 epochs and a batch size as 256. After running that we will get seriously it took a lot of time earlier, but you have to change the runtime type as GPU to make it a little bit a shorter time. So yeah, after doing that we will plot the graph to make it more to understand more clearly, because by seeing the number it's very difficult to understand. Here is a bunch of code to show the graph, and here is it. This is the graph. The blue line is the training accuracy and the red line is the validation accuracy. As you can see, the validation accuracy reaches a maximum to around a little bit more than 0.6, something like 0.62 or 0.63, and after 10 epochs it becomes almost constant. Now the question arises is, did the network presented the signs of overfitting? So by seeing this graph, yes, it actually showed the sign of overfitting. And after around 10 epochs, the validation accuracy leveled out, but the training accuracy, it went up all the way to approximately 0.97. So yeah, the model did show the size of overfitting. Now how many layers we used in this model and identify their types. So as discussed earlier, let me show you. We used 5 layers: convolution, max pooling, flatten, a dense layer with ReLU activation, and a dense layer with softmax activation. So here I have written that same thing. In the question 5, we need to explain the purpose of each layer. So convolution layer, what is this used for? To extract information. Max pooling layer, it's runtime disconnected, reconnect. Max pooling layer decreases the spatial size of the input picture by taking the maximum value of pool. The flatten layer, so what does this do? Flattens the preceding layer output into 1D array, which is very important to feed the output into the dense layer. And as discussed earlier, what does the dense layer do? It's a connected layer of a neural network which computes and forecasts the input of the picture, and the another dense layer which is the softmax one, which gives the probability distribution. Now after that, what we need to do is we need to add one or more convolution layer to the model. So as you can see, I have added one more convolution layer, and after running that using the same configuration as a previous one, yep, so as you can see, the validation accuracy became quite near to 0.7. Earlier we were getting around 0.63 or something, but here now we are getting around 0.68 or 0.69. By comparing the two results, now what we can see the difference is adding more convolution layer increases the validation accuracy. So, and after around 20 epochs, it became a flattened. Till then it was just increasing and increasing, but in the earlier one, at around 10 epochs, it became a flatten. So that's the main difference between the two of them. Then what we need to do is we need to add a dropout layer to the model. So for adding the dropout layer, we will use dot dropout, and we will pass a 0.5, that is the weight of the dropout layer. And then again, using the same configuration as above, training our model. So as you can see, the training accuracy and the validation accuracy, it's almost similar, going with the same trend, but this time the training accuracy is around 0.7. Earlier we were getting around 0.9, approximately 0.98 or 97, but this time it's very low. So now we have to explain what the purpose of the dropout layer is. So it is reduced. It is used to reduce the overfitting. As you can see, the overfitting is now reduced, but the accuracy of the model is compromised. So if we want to create a model which is less accurate, but to reduce the overfitting, then you can go with the dropout layer. So how does it work? So when training the data, the dropout layer chooses certain number of neurons and just removes that from the model and replaces that with a bunch of zeros, so that and the spaces of the removed neurons is compensated, and all the neurons are active during the testing, but their output is scaled down by the dropout probability, which aids in achieving the same outcome as during training. And last but not the least, in the question 10, what we need to do is we need to change the model, whether in the layers or with the weights of each layer, and we need to improve the model's accuracy. So for that I have added two or in total 3 convolution layers, each one with the different weights, then a max pooling layer, then a dropout layer, and then 2 dense layers with ReLU functions with different weights, and a softmax layer. Again, compiling our model and then training our neural network, we can see that the training accuracy is became pretty fast, and it gave the accuracy of 0.98, and the validation accuracy, as we were getting earlier in the second part, was around 0.68, but now it is 0.75, which is pretty good. The validation accuracy also increased this time, and the overfitting, it starts at epoch 10. So yep, adding more layers to our neural network makes our accuracy more. So that's pretty much it about this assignment. I hope you guys enjoyed. Thank you very much for listening, and have a good one.